Hello, everybody, and welcome to the 35th PyData Trinidad and Tobago. Today, we will be getting an amazing presentation from Akil Hosang, where he's going to be covering how to use LLMs for small island developing states, such as Trinidad and Tobago, to address climate change. We're going to jump into the code of conduct, and then we'll dive into the actual introduction. So, as you are here, we do ask that you do not insult or put down others. We do ask that you behave professionally. And remember that sexist or harassing, racist, or exclusionary jokes are not appropriate for non-focus. All communication should be appropriate for a professional audience, including people of many different backgrounds. So, as I said before, we have Akil. He has a master's and is a graduate from Florida Institute of Technology. There, he primarily studied machine learning and artificial intelligence. Within the field, he particularly enjoys reinforcement learning, information of things, and ML applications in sports. Outside of AI, he also enjoys completing small personal projects like game development, plays in sports, and he loves music. And today, Akil is going to be talking about how small island developing nations such as Trinidad can look at how climate change uniquely affects them. We will look at that first, and then we will look at our idea on how we can help combat these effects using LLMs. We'll also be exploring how these LLMs technically work, where they apply, and the techniques alongside LLMs and these techniques alongside LLMs will also be discussed. Finally, we'll briefly look at the progress of this project, the current direction, and what we hope to accomplish in the future. So Akil, take it away.
Thank you so much, Tareen, for the introduction. And hello, everyone. I'm Akil Hosang, as you just heard. Today I'm presenting on LLMs and climate change. And this is a project that I did through TT Lab. Well, not me alone. I work with a team that's constantly changing in size here and there. But at the time of the research that we did and the paper that we put out, there was about 5 of us on the team. And so I'll get into that now. Firstly, the team members are here. We have Dr. Addison. She helped spearhead and take control of a lot of the work on this project, as well as the other teams here, Timia, Chris, and Professor Hosang. And my contribution on this, I worked particularly with the LLMs, understand them, get to know how they work, and then applying them on some techniques so that we could put together a system that we thought would help combat climate change in our own particular way. So first we'll look at small island developing states, a little bit about them, and then we'll get into the large language models. The main technique that gave some uniqueness to this project, retrieval augmented generation. And then finally, just touch on where we are now a bit and some of the things that we're looking at. So first of all, we'll start with the introduction of small island developing states, or SIDS. And so what are SIDS? SIDS are a group of about 39 states and 18 members of the United Nations Regional Commissions. This is their official description of them from the United Nations. And these particular states, they face unique social and economic and environmental vulnerabilities. And even though there's no direct or specific quantitative characterization for SIDS, so there's not any definition by size or by population, they could be recognized by some of those features. They tend to be a certain size, tend to have a certain population. And altogether, they actually make up a little less than 1% of the population of the world. And like I mentioned before, there's some unique vulnerabilities, especially climate-related issues. An example of some of those islands, of course, Trinidad and Tobago. And then there's also Guyana, but those classifications of SIDS don't exist only in the Caribbean. They also exist for countries in other parts of the world. So SIDS are vulnerable for multiple reasons. One being the fact that they are low-lying coastal nations. So something like the small increases in sea levels could affect flooding greatly in these islands. And research actually showed that from like 2000 to 2023, there were close to 800 climatic events impacting the Caribbean region specifically. And tropical storms and floods made up about 50% of those events. So floods really pose a big hurdle or a big, how to call it, event for us in the Caribbean and for those in small island development states. Also, their small land area means that space for things like relocation or infrastructure is not not as viable as other places that have a lot more landmass. They can also suffer from education and literacy gaps related to climate-related issues, and that can affect how effectively people respond to these alerts or any kind of warnings. And for states that typically rely on climate-sensitive sectors like tourism or agriculture, we saw it as an important point to try to look into such a problem and see how we could contribute to that. So, like I mentioned earlier, one of the problems we have to face has to do with communication. And there's a lot of different things that pop up here and there. Given that in the case of climate events like flooding, communication could be slow, could be generic, or just plain inaccessible. So there might not be a system for a lot of small island development states. There might not be any kind of system that people could rely on or get information, critical information that they need. So given the potential human and economic losses that SIDS could face due to the unique communication challenges, the question is, how can we reduce this loss and improve the communication? And in our case, we looked at how we can leverage artificial intelligence and large language models to address this problem. So here is where we talk about large language models a bit. And at the height of the intelligent chat models right now, we know there's a big buzz. It's over the course of a couple of years, it's made huge sweeps. So I know everybody's interfaced with one to some degree. And so we decided to leverage this the informational and communicational power of large language models. But what are they? So technically speaking, they're from a group of deep learning architectures called transformer networks. And these transformer models are like neural networks, and they learn context and meaning by tracking relationships in sequential data. So for example, like the words in a sentence, the way they sequence and order in a sentence, it gives them meaning and context. So put simply, they're AI systems that can understand and generate human-like text. And then we can leverage that to be used for a lot of things like translating language or summarizing large bodies of text. And in our case, we use it as an educating and informational tool to educate people about flood risks, especially in places where standard methods don't work. So being able to apply this technology, it could go a bit more than even educating, and it can serve in certain ways, as we'll see later, as a means to set up alerts, maybe schedule important meetings with the people that deal with climate issues and disaster issues and stuff like that. So simply using a large language model in the system, it could serve some purpose for sharing and educating the public on climate in general, but it won't do an effective job with giving information on recent or changing information. So, for example, the models by themselves are able to are trained on a lot of data, and they're able to answer questions across many fields. But if we try to leverage information that might change a lot, or is only important when it's recent, so something like weather, um, then it might have a harder time being able to leverage the models by themselves. So that being the case, it won't serve well to help the public react to climate events like current flooding, the models by themselves. So in our work, we propose a system to utilize different streams of information, such as official climate documents for Trinidad, as well as sensory data that stream different flood-related metrics. So the idea was alongside large bodies of information about local climate, we can also set up different sensors to track maybe rainfall, to track the statuses of rivers, and that will give us a good idea of gauging maybe flood events. The thing is, the models by themselves don't react to new information, and it's computationally expensive, and it takes a long time to retrain the models with new information. So that's why we utilize a technique called retrieval augmented generation, or RAG for short. And this supplemented our large language models and our entire system. So I'll talk a bit about RAG now. Apologies, I'm not sure where the labels for these diagrams are, but I'll get into explaining it, and hopefully it makes a lot of sense. So RAG, or retrieval augmented generation, is a technique that enhances these large language models by integrating them with external data to improve the accuracy and the context and the relevance of the output. So like we talked about before, the models are trained on a lot of data and information, but things that might change a lot, we're able to use this technique to bring them in and give the model more context on recent or changing information. So this method allows large language models access to information and context they didn't previously have. So this technique works by preemptively taking our data. So if you follow the diagram from the bottom left, we have our data, and we preemptively store it in a database, specifically a vectorized database in our case. And when a message is sent from the user to the model, so from the top left, you see the user might send a query to our model. And when it sends a message from the user to the model or system then does a search on the database for information relevant to the request for context. So for example, if someone queries our model for information on flood related information, and specifically in the area of Arima, the system then checks the database for information or context related to Arima, and using the different algorithms is able to grab different bits and pieces of context, and it decides what's important, and then it takes that information and adds it on to the initial request. So it's sort of like if you picture the system or these language models in isolation, it can take in a query about, say, a flood event, but it might not be able to tell you what's currently going on. But using the RAG technique, it then adds on stuff from our database. So our sensors might know the gauges of the river are really high, or the rivers are overflowing at this point, and it could even use maybe cellular data or social media data, and all of this serves as context for the model. And this context then is added on to the query and then sent to the model. So the model now knows the question and then the context. And that is how it's empowered to have a stronger idea of what's going on and to reason. And then that output is sent back to the user. So the user has a better idea of what's going on. So that's the general idea for retrieval augmented generation, and that's what we use in our system. So there's another question of retrieval augmented generation versus another technique called fine tuning, and this is an alternative method that was mentioned a little bit before. And this in fine-tuning involves training a large language model on smaller, specialized label data and adjusting the model's parameters and different embeddings based on this new data. If this method was used done using the data collection, it's worth it to mention that it would work. This is a valid method, and it might even produce output that might seem more accurate. But the thing is, accuracy wasn't the only thing that we valued. Fine-tuning, it takes a lot of time to train this model or retrain this model on our localized information. It's computationally expensive, and to be able to do that on real-time data that might change by the second. So like sensory data changes even quicker than per second. And so that wouldn't be practical or effective. And by the time the model could retrain on all of our new data, it's possible that by then it's obsolete, or it's at least not effective or accurate for the needs that we have. And that is where RAG, or retrieval augmented generation, is a strong option. It doesn't force the model to relearn things. It just finds the context from the data that we have and gives that to the model. And it's worth it also to mention that though these in our work, we use the RAG over fine-tuning, they don't necessarily need to exist separate from each other. Fine-tuning is really good for specialized areas, domain-specific areas, and it's highly accurate and efficient in these technical areas. And it's worth using, or it's possible to use it in conjunction to learn static data that doesn't change a whole lot, while supplementing it with our RAG technique. Well, the RAG technique, I won't say our RAG technique, but the RAG technique to learn data that changes and moves a lot. And those two in conjunction can be really powerful. And yeah, that's an idea that we will even look into in the future part of our work. So to go from here to our results, or the results of the work that we've been doing. Oh yeah. Oh, sorry, these, let me pull this back up. Yeah. So for our initial experiment and the proposed proof of concept, we use a few heavy climate-related documents. There were two main documents, but these were very informationally dense documents related to climate specific to Trinidad and Tobago. And then we asked the model specific questions related to the documents that we had, and we compared it to information from LLM outside of our system, like ChatGPT. What you see here is the output of our system. So we asked it some simple questions like, what does the acronym for WASA stand for? Can you explain DDI? And a question on the loss in US from flooding in Trinidad. And these are questions, or this is information that was listed in these PDFs. And in our comparisons, ChatGPT was able to answer a few, but not nearly as much as the model that we had. If I remember correctly, we asked the same questions, and for the acronym for WASTA, I was able to answer that. But for explaining what DDI is in relation to climate, or something really specific like the loss in US from flooding in Trinidad, it had less context. And that's because, this is a lot of information specific to Trinidad as well that might not even be publicly available. And so, there's no way that a model like ChatGPT could know the information if it's just simply not out there. And that's a really strong benefit of using RAG in our system, that if we're able to work together with different organizations and get certain data, then it proves really useful if those organizations are tracking important metrics when it comes to climate and those things. And so that's the results of the paper that we worked on. But we have been working on this idea a lot more since adding the tie on the paper on this. And I want to talk a bit about what we call agentic LLM systems. So this is sort of adding even more on top of that basic system that we described before. So the educational and resourceful benefits from such a system are already great to see, but our system isn't done there. And the great potential can be found in implementing agentic LLM, like an agentic LLM architecture. So what if, rather than just receiving a message saying where is flooded when querying the model, the system would then send an interactive map showing the actual area that has been affected. Then it could also recommend steps to take depending on where you live, and even send you GPS routing for a better path to take, say on the road, and they're stuck in traffic, or you recognize that there might be flooding somewhere, there might be a big hole up somewhere, and you're hoping for a better route to take to avoid the flooded roads. So that's the power of utilizing an agentic LLM system. So the agentic system are models that don't just answer questions, but they also are able to act. So these agents can automatically generate alerts, maybe schedule like a community meeting, etc. But there's no limit to the kind of actions it could take. It's only up to the person that's building the system and the tools that they have available to them to add in these different things. So they have the capability of multi-step reasoning, where it breaks a task into steps and then it executes them in order. It can also call APIs and fetch documents and many more. It also remembers past steps and adapts based on new information. So having such a system is greatly beneficial to adding a feature-rich environment that can sufficiently assist with climate and flooding events intelligently. So being able to, right now we're also working on using social media data. So maybe the content of a post, somebody might go on Twitter or Facebook, or I guess not Instagram, Twitter or Facebook are good examples. And we can maybe use the content of their post if it's related to flooding, and even maybe the location that post was made from. So say a flood is occurring in Port of Spain in town. And this is something people might talk about on Twitter, they might talk about on Facebook, and that is also a way or a metric to be able to tell what's going on and to be able to capture that information and add it to our database and to be able to let the model use that as context of what's going on, is also really important and it really helpful. And in this agentic system, it can be set up to build more reason from this. So maybe you know it's flooding, or maybe sorry, you it's not flooding, but you see certain posts on social media, and those posts on social media conflict with what's actually going on. Having the intelligence of an agentic system and it's able to query, okay, this is being said on social media, but this is what our sensors say, and this is what the what we infer from cellular data say, and all these things, is able to make smart decisions and say, okay, even though persons are saying this, maybe that's not necessarily true. Or maybe if this one source is wrong, this is right. So being able to make those type of decisions as well is really important. And this is something that we're working towards. So, and as well, as I mentioned, the sensory data is also very important. Adding those all into the system allows it to make very critical decisions. And that is where we're at right now. Adding in this architecture to further facilitate more features for the general public or for the users of this system, so that is better able to educate them, but also give them tools to figure out how to navigate these events better, specifically flooding. So that is the summary of the work that we've been doing. And yeah, thank you very much. Is there any questions or any points that I might have missed that somebody might be interested in or want to expand on?